So the goal of this video is just to learn some circuit symbols and also look at how we measure current and voltage with ammeters and voltmeters. So first, just some common ways we draw things in a circuit. If you're drawing a battery, you'll draw it like this. This would be one cell of a battery. You can put multiple battery cells together just by doing this. It'd be like, there'd be 3 cells of a battery all together there. The tall side here is the positive side. So that's the positive side. That's the negative side there, the short side. So that's your battery. A light bulb in a circuit we usually draw just as a little X. So that means there's a light bulb. A switch looks like a wire that's been cut open. So that is a switch there. And a resistor, we draw like a little squiggly, jagged kind of line like that. So that's a resistor. And if you just have a regular old wire, we just draw that as a straight line in your circuit. So let's try redrawing this circuit with our circuit symbols. So you can see the battery has a positive end there and a negative end there. So I'll draw the battery first with the positive side over here. And then this goes next to a switch. So I'll put in my switch symbol like this. Then from there it goes to a light bulb. So I'll put in my light bulb symbol. And from there it goes back to the battery. And that would be the circuit redrawn with symbols. You can tell that this is a little bit easier to understand than this picture here. This is practically what it looks like when you build the circuit, but this is just a little bit easier to work with and draw and do some calculations from, which is what we're going to do next. So let's say you have a battery. So this is a 2-cell battery and it has 12 volts. So I often just write that right on my picture, so 12 volts. We also know that there's 2 amps of current flowing around the circuit. So that means that the current through the battery is the 2 amps. So I'll say this is delta V, often we use T for total, and the total current, I total, is 2 amps. So that's the current and the voltage at the battery. And what we're going to try and find is the resistance of a single resistor here, R. So we could easily find R total, right, from just the battery. So if I know this equation, delta V is IR, I can make that equation specific to one light bulb or one resistor, or also specific to the total voltage, the total current, and the total resistance. So let's rearrange that for R total. Just divide both sides by I total. And we'll have R total, so that cancels the I there. R total is going to be delta V total, like through the battery, divided by I total. Plugging in your numbers here, delta V is 12, I is 2, so that means the total resistance is 6 ohms. So that's my R total around the whole circuit. But I want to know not just R total, but R through a single resistor. Now what we're often really tempted to do here is say, okay, well the total is 6 ohms, so you know the resistance through one resistor must be like, there's 4 resistors, right? So we just take 6 and divide by 4. That's totally wrong because these resistors are in parallel. So it's really important that we look at how the resistors are connected. Are they connected in parallel? Are they connected in series? Are they connected in like a little bit of both? We have to really worry about that. So these resistors are all in parallel with each other. So that means that a single electron could take this path here, or this path, but it doesn't have to go through every resistor, and in fact it won't. It'll just follow one loop. If I were to draw the path of one electron, it would look something like this, or we pretend it's protons that move, so they would move this way, would go around like this, and go through this resistor, and come back to the battery. So that might be one path that they take. Maybe a different proton would go like this. It would go around here, and take this loop here, and then come back to the battery. Like this. But it wouldn't, that single proton is not going to go through both resistors. So actually having 4 resistors here makes the overall resistance less than it would otherwise be if there was just one resistor. If you made it this circuit here, the total resistance would actually go up a lot. Okay, so what do we have to do to figure out the resistance of a single resistor? We need our parallel resistance equation, which is this one. So 1 over R total is going to equal 1 over each of the resistors that are in parallel, and there's 4 of them. So 1 over R plus 1 over R plus 1 over R plus 1 over R. Now thankfully they're all the same resistance. They all have the same resistance R, so that makes this equation easier. So 1 over R total is just going to equal 4 over R. There's 4 of them, so 4 times 1 over R is 4 over R. Trying to rearrange this for R here, so I could cross multiply and I would get R times 1, which is just R, equals 4 times R total. I've already found R total is 6 ohms, so now I know a single resistor is actually 4 times the 6 ohms. So maybe the opposite of what we would intuitively think, that it's a quarter of 6, it's actually 4 times the 6 ohms. So that would be 24 ohms, and it looks like 2 sig figs is good, so I'll keep just the 2 significant figures there. So one of these resistors on its own is 24 ohms, but when you add all 4 of them in parallel, it drops the total resistance to only 6 ohms. All right, let's look at batteries in series next. So for this, if you have 2 batteries stacked on top of each other, the key is you have to stack them properly. So you need to stack your batteries like this. So that would mean positives are both pointing this way. If you were to stack batteries like this, one this way, they'll push against each other and just cancel each other out. So if you've ever put batteries into like a flashlight and you put one in with the positive going forward and then one with the positive going the wrong way, then your flashlight won't turn on, it won't work. So you have to make sure they're going in the same direction. And if you do that, then their voltage just adds. So it's really nice if you have 2 batteries in a row like this, not like this. Then whatever the voltage of a single battery is plus the voltage of the other battery will make the total voltage of your sort of battery set there. All right, now we're going to look at how do we actually measure things like current and voltage. So current is measured using a device called an ammeter. And when you're connecting an ammeter into your circuit, it's really important that you always put it in series in a circuit. So if you want to know the current through a certain light bulb, you need to put the ammeter in series right beside that light bulb. Or if you want to know the current in through the battery, you'll want to put the ammeter in series with the battery. The circuit symbol for an ammeter is kind of what you'd expect. It's just an A, so it kind of is easy to remember. So if you see an A with a circle around it, that means an ammeter. Why do they have to go in series? Like, why is that so important? So you have to think about what is an ammeter measuring. It's measuring current, and current, if you remember, is how much charge goes by a certain point in your circuit per second, per unit of time. So if I want to count how much charge is going by, I need to literally stand in the circuit to count how much is going by me. So I like to think of an analogy to someone who's trying to count how much salmon is jumping up a river. So they're not going to like look far away and stand on a hill somewhere far away. They're going to like put on those tall boots that keep their feet dry and step into the river and count, well, how many salmon are going by me at this point in the river. So I made a little device for us to kind of imagine we're counting salmon. If this wire is an actual wire, and these are the little electrons in it, if you want to know how much charge goes by, say this point per second, you're going to want to stand in that point as a little counter and count, okay, 1, 2, 3, 4 coulombs of charge went by in a second. That's what an ammeter is going to do. It's going to stand right there, right inside the circuit, in series with whatever you're looking at to see how much charge goes by. All right, let's see what that looks like in some actual circuits. So here's a circuit with a battery and an ammeter in here. So what would this ammeter measure the current through? Well, it's right beside this bulb here. So that means the ammeter will measure the current through this light bulb. So the ammeter will measure, oh, light bulb, it's a B. The ammeter will measure the current through whatever it's in series with. Here, the ammeter is in series with the battery, but it's not in series with this light bulb. See how this light bulb, you have to kind of slit past there, right, to get to that bulb and that bulb. So those are not in series at all, but it is in series with the battery. There's no sort of splits between the ammeter and the battery. So this will measure the current through the battery. So that would be one way to set up a circuit to get the current through the battery. You could have also put the ammeter over here. That would have worked too, right? You could put it on either side of the battery as long as it's in series with the battery. Here, we have an ammeter that's set up in parallel with the battery. It's also in parallel with this light bulb. So what's going to happen here is that this will actually short circuit. So a short circuit is what happens when you have a battery connected to itself with basically just a wire or something of very, very low resistance. So we'll jump ahead and then jump back. The resistance of an ammeter has to be very, very close to 0. The reason for that is that you don't want your ammeter to change the circuit, you just want to measure the current through your circuit. So what you're trying to do here is like count how many beads are going by without actually changing the speed of the beads as they move. You're trying to count how much current is flowing in your wire without actually slowing it down or decreasing how much current goes through a certain area. So if you have your ammeter here, right, nicely in parallel with this bulb, we want to have 0 resistance of our ammeter, so the same amount of current would flow through that bulb whether the ammeter was there or not. In this case, the ammeter is in parallel with the battery, and there's nothing else, no other bulbs that are in parallel on that little loop here. So the electrons, they're not going to take this path through this bulb at all, because that bulb has high resistance, so why would they take the path of high resistance? When they have a path they could follow here, which is almost 0 resistance. And that path is basically equivalent to this path here, the path that has basically no resistor on it at all. So the electrons, or we pretend it's protons, the protons start going around that circuit really, really fast, and there's nothing to stop them. There's no resistance at all. So they drain your battery really quickly, and that heats up your battery. It's actually really dangerous, so you can light your battery on fire. So not something you ever want to do. Don't ever put an ammeter in parallel with the battery. So don't do this. It's really dangerous. If you have an ammeter, you want to measure the current through the battery, it needs to be in series with the battery, just like this setup here. All right, potential difference. So if we want to measure potential difference or voltage, we use a thing called a voltmeter, kind of an intuitive name. Voltmeters, though, are always placed in parallel with whatever you want to measure the voltage across. The symbol for a voltmeter, very much like an ammeter, we put a V in a circle. The reason why voltmeters have to be in parallel is because they're measuring a potential difference. Think about a potential difference as being like a height difference. So say you have a mountain here, and you want to know how high the mountain is. Well, you're not really going to be able to tell by standing on the mountain itself. Standing at one point on the mountain isn't going to tell you the overall height. You need to step back, way over here and look at the height here and look at the height there, and then you can measure the distance between them. And that's essentially what a voltmeter is doing. You need to be connected at point A and connected at point B so you can measure the difference in potential between those 2 points. So here's an example of a voltmeter that's in parallel across the battery. It's also in parallel across this bulb. So see how this voltmeter attaches basically on either side of the bulb and attaches on either side of the battery. So it will measure the voltage across the battery and the light bulb. So this is I keep messing this up. The light bulb with the B forwards. So the voltmeter here will measure whatever it's in parallel with, which is the bulb. It's also the battery. This picture here, the voltmeter is just in parallel with one bulb, so it'll measure the voltage across just this light bulb here. In this picture, the voltmeter is in series with the light bulb, and it's also in series with the battery. So this whole circuit would just not work. So you're not going to get a short circuit, dangerous kind of situation like with the ammeter. A voltmeter actually has a very, very high resistance. The reason for a voltmeter having such a high resistance is that you don't want to change your circuit, right? So I want all of those protons to flow through this bulb like they were before. If this voltmeter had a low resistance, then all of those protons would skip the bulb and just jump across on the voltmeter instead of going through the bulb. So we need a really high resistance voltmeter to basically not change our circuit at all and force all the protons to keep going through the bulb and not skip and go around through the voltmeter. So because of that, if you put a voltmeter in series in a circuit instead of in parallel, then when the current tries to flow through here, it can't because the resistance is just too high. So it just shuts everything down. So this isn't going to cause a fire, it's just going to make your circuit stop working. The light bulb won't turn on, just nothing will work here. So let's just write that down. The resistance of a voltmeter needs to be very high. so that the circuit remains unchanged by the addition of the voltmeter. So our goal whenever we're measuring voltage or current is not to actually change our circuit, right? We just want to measure what's going on in our circuit. So if I have a really high voltage and I have some sort of a setup like this, then I'm not going to cause any current to skip the battery here or skip this light bulb here. It's going to just go through as it usually would. So let's look at series and parallel circuits separately, just a sort of reminder of how voltage works. Remember that it's a potential difference. Thinking about it as like a height difference on a mountain is helpful, I think. So if you gain, say, 3 volts at a battery, and then you're looking at a series circuit, then if you gained a height of 3 meters, and you have to go all the way around like a loop, maybe a roller coaster loop, and you lose 1 meter with the first sort of cool hill, then you're going to have to lose another 2 meters to get back down to the bottom. Or in other words, voltage is shared in a series circuit, although not always shared equally, right? This bulb used less voltage than this one. The key is that if you went up 3 volts at the battery, you have to go down 3 volts by the time you get back to the battery again. In a parallel circuit, the sort of height analogy still works, but you have 2 separate loops you could take. Either you could go up the battery here and then loop around through this bulb and back, or you could go up the battery and loop around through this bulb and back. So your loops are either like this or like this here. So if you gain 3 volts at the battery, then when you go through this one light bulb to get back to the battery, you have to lose all 3 volts to get back here. And if you take this loop, you still have to lose all 3 volts to get back to the battery. So this means that the voltage for 2 light bulbs that are in parallel with each other has to be the same as the potential difference across each bulb and across the battery, if that's the only thing in your circuit.